when Reese Harvey and I were originally working on this, we were kind of looking for forms that would have, these nice properties, and I think what we ended up doing was finding this very explicit form, which was a total mystery, and we proved it had all the right properties. It took sheets and sheets of reams and reams of paper. And then finally, months later, we figured out the right way to do it. And so today you'll see the right way to do it, but it's not the way it was found. So to begin with, I'm going to remind you about the properties of the Cayley numbers. So standard notation is that these are the real numbers and the complex numbers. H will stand for the quaternions, and blackboard O stands for the octonions. Okay, now in all of these cases, these are algebras over the reals, with an inner product on them, a positive definite inner product, and with a conjugation map, mapping the field, so this stands for F, mapping the field into itself. It's an involution. Square is the identity. And it has certain properties. I mean, multiplication, the product of xy has length, which is the product of the lengths. If you take xy and take its conjugate, this is y bar x bar. Another property is that the inner product, multiplication, is sort of skew adjoint. If you multiply on this side by z, that's the same as multiplying on that side by z bar. Okay? Now, there's something called the Cayley-Dickson process that generates these things, so I should remind you about this. The Cayley-Dickson process is the following. I mean, suppose you start with an algebra with these properties. So it's an algebra with, an inner product, and with a conjugation map, etc., satisfying these nice properties. Then you can define a new algebra, A plus A, and on here, multiplication is given as follows. The product of AB and CD is this, I have it written down here somewhere. Is given by AC minus D bar B, and DA, this is not a memorable product, BC bar, okay? And on the other hand, a new conjugation is given by taking the old conjugation on A and just minus B. Okay, and you can verify that, at least, so let's take this process, and then what happens is that inductively, if you start with the real numbers, you get the complex numbers, you then get the quaternions, and then you get the octonions. Okay? In this way. So the octonions are simply the two copies of the quaternions with this multiplication. Now, it's well known that the quaternions are not commutative. Of course, the complex numbers are commutative. Quaternions are not commutative, and the octonions are not even associative, and that this process dies at this point, right? After this, it's not an algebra of any sort. Now, on the other hand, the octonions, while the octonions are not associative, they have some nice properties, and one of the most useful properties is a theorem due to Artin, which says that the subalgebra of the octonions generated by with unit generated by any two elements is associative. And as a matter of fact, it's a subalgebra of a quaternion algebra. By a quaternion algebra, I mean a subalgebra of the octonions, which is isomorphic to the quaternions. Okay. So this is useful, as you'll see in a moment. The other thing that's useful when it comes to discussing the octonions are the so-called Mufang identities. So, I mean, this is a devilish algebra to work with, and so what little structure it has is useful. So the first Mufang identity is the following. If you multiply x, y, x, I'm not worried about I don't have to worry about how things associate because this is in an algebra generated by two elements. And then multiply by a third. Okay, this is the same as multiplying z by x, and then multiplying by y, and then multiplying by x. Okay, and the same thing holds on the right. So if I multiply x, y, x like this is the same thing as putting z multiplying by x, then multiply by y, then multiply by x again. So this is, so left multiplication by x, then y, then x is the same thing as left multiplication by this product. And the last Mufang identity is that if you multiply x, y, zx, this is the same as x times yz times x. Okay. So when you want to show that spin 7 acts on the octonions, these are really useful to have. Now that said, let me talk about the things that are really important for calibrations, and these are the so-called cross products. Cross products on the octonions. Okay, there are three of them. One is a cross product for two elements, x cross y, and by definition, this is minus 1/2 x bar y minus y bar x. And then there's x cross y cross z, which is by definition 1/2 of x y bar z minus z y bar x. And then there's the fourfold cross product, which is 1/4 of x, and here we have yzw, y cross z cross w, plus y bar times zxw, and z bar times x cross y cross w, and w bar times, oh, this is an x bar in the beginning, yxw, y cross x cross z. Okay? So this may look reasonable. This looks a little less reasonable. This is perplexing. But these products, I mean, there are better ways of saying it. I mean, you could say take something like this and alternate it, take something like that and alternate it. But then you can use the identities in the quaternions to reduce down to these simpler expressions. Okay, so this is really somehow the alternation of that object. And this is the alternation of that object. Just sum over all permutations with a sign. But then you want to normalize. Now, there are two really important things about these products. First of all, they're all alternating. So they're clearly, multilinear, but I claim that if you set any two equal, then you get 0. So it's clear for this, right? And it's also clear from this that if you set any two, you just look at the three possible cases. If you set x equal to y, or x equal to z, or y equal to z, you get 0. And the same thing is true here. So these are actually skew linear forms, but the most important fact is that they have the following property, namely the length of the vector x cross y is the same as the Euclidean length of the vector x wedge y. The length of the vector x cross y cross z is the Euclidean length, well, it doesn't matter of this simple vector in the norm that I first discussed. And the same thing here. Cross z cross w is equal to x wedge y, wedge z, wedge w. So if these are all, if you take an orthonormal pair or an orthonormal triple, then you get 1. Okay? So now, the idea is the following, that if you take the real part of any of those cross products, well, the first one isn't very interesting, but you take the real parts of the other cross products, you get a form. So I mean, write any component, but the real part is always a well-defined object. The real part is a form whose the length of the real part is certainly less than or equal to the total length. So it's less than or equal to this. Hence, it's a calibration. So the real part of each of these is a calibration. And furthermore, the equations for when you get 1 are exactly that the imaginary part be equal to 0.
Can you define the part of basically
Not to my knowledge, no. I mean, there might be something which is, I don't know. If it were there, it probably would be related to the threefold product somehow. But, I don't really know, actually. So the idea is the real part is a calibration, and the imaginary part is the equations gives the equations for defining the planes. So I should say so let's look at what the real parts are. The real part of x cross y is 0. That's always imaginary, as you can see by just taking the bar of it. Okay? But the real part of x cross y cross z is an interesting object, particularly when x, y, z are all imaginary. It looks like this. It's x, y times z if x, y, and z are purely imaginary quaternions. In fact, what it is in general is exactly this, but you have to take the imaginary parts of x, y, and z. And the real part of x cross y cross z cross w is the inner product of x with the triple cross product, y cross z cross w. And so then I should say what the imaginary parts are. So the imaginary part of x cross y is equal to 1/2 xy, the commutator of x and y. I guess this is a... Yeah. So this is the commutator, xy minus yx. I guess I want x and y to be in the imaginary part of O. That's where it's going to be interesting. If I take the imaginary part of x cross y cross z, I'm going to get 1/2 of the so-called associator, which we write this way. And this is by definition. So what's the associator? It's the thing, which way does it go? It's like xyz minus xyz. I may have this wrong. It's either that or the opposite way around. It's the opposite way around. xyz. Again, for xyz, the imaginary part of O, and the imaginary part of x cross y cross z cross w is equal to 1/2 x, y, z, and w. This is called the co-associator, and this is given by equations minus. Maybe I won't write this down. It isn't all that important. I'm going to save time. So they'll be in the notes, so I'll leave it for that. But it's a fourfold term. It looks like minus 1/2 y inner product with zw times x plus 4 more terms of that sort, which is not particularly illuminating. But you notice that this is, so these two objects are really nice. This is the commutator, which is a classical object, and this is something which is 0 if the algebra is associative, obviously. And the interesting thing is that the associator in this case is an alternating form. And algebras for which the non-associative algebras for which the associator is alternating are called alternative algebras, and they've been studied because they have a lot of nice properties. Okay, so so now what we want to do is to just look at these in a little bit more detail. So let's begin with associative algebra. Associative geometry. So here I'm going to be looking in Euclidean 7 space, which will be identified with the imaginary octonions. Okay? And we're going to define this calibration phi to be equal to the exterior form, which when it sees 3 imaginary Cayley numbers goes, which way is it? X times yz times y dot z. Okay, I mean that's pretty straightforward. The interesting thing is that this is skew symmetric, right? As you can check from the things that I put down. Little exercise, anyway. It certainly follows from the assertion that all these things are alternating. Okay, and now it's clear that as I've said already, simply from this important fact, this is a calibration, but we can see exactly what happens. I mean, if I take phi and apply it to an orthonormal triple of vectors, then what am I going to get? Well, this is E1 times E2 dot E3, right? And if I take the absolute value, well, and so this is what? This is less than or equal to E1 times E2 dot E3, and this is equal to 1 if this is an orthonormal triple. And when do you get 1? You get 1 exactly by the standard equality and the Schwarz inequality if equality occurs if and only if E1 is equal to E2 times E3. Okay, now this is an alternating form, so I can take any oriented orthonormal basis. And so you see that the three planes, the three-dimensional planes on which this is equal to 1 are exactly those planes where if you take any two vectors and take their product, that's again in the plane, okay? And the orientation, E1 is equal to E2 times E3, is the orientation of that plane. Okay? So now what are such planes? These are, I mean, again, if you think about it for a second, these are the three-dimensional subspaces which are exactly the imaginary parts of quaternion subalgebras. Because if you have this property, then this defines a quaternion subalgebra. And so you see that you get equality if and only if so we have equality if and only if span of E1, E2, E3 is the imaginary part of a quaternion subalgebra. Okay, so also we see by going back to this cross product. So I take the triple cross product, and from the triple cross product, phi of x, y, z squared, that's the real part, plus the imaginary part, which is phi times the length of x of the alternator squared, is equal to x wedge y wedge z squared. Okay? Because this is the real part, and this is the imaginary part. Okay? 1/2 of this imaginary part. So what does that tell you? It tells you that this is equal to plus or minus 1 if and only if this is 0. And that means it's an associative algebra, and an associative algebra is a quaternion subalgebra. Okay? So you see that phi of x, y, z is equal to x wedge z. That's the condition for the calibration, if and only if the associator vanishes. And we conclude that the Grassmannian for this calibration is exactly equal to the canonically oriented imaginary parts of H subalgebras of O. And these are the three planes where this is equal to 0 with the appropriate orientation. Okay. So now, 'cause, 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 ' maybe I should just go under here for a minute. Now, another thing that's obvious is that if you look at the group of automorphisms of the Cayley numbers, so this is commonly called G2. This is the group of algebra automorphisms of O. Then the automorphisms preserve, well, the inner product is defined as the real part of x times y bar. So automorphisms preserve the inner product, and they clearly preserve multiplication, and so they preserve that form. It preserves phi, and as a matter of fact, it's clear that it's actually equal to, so forget about preserve, it's actually equal to the elements in O7 such that G star phi is equal to phi, because phi defines multiplication, right? If you think about it, that 3 form is exactly defining the multiplication. Okay, so any automorphism preserves it, and anything that preserves this form must be an automorphism. Okay? And so therefore this group acts on the space of, these are called the associative 3 planes. And so it turns out that the associative 3 planes are actually a homogeneous space if you pick one point where the subgroup is SO4. The isotropy subgroup preserving a plane is SO4. And in fact, you can say what the action is. SO4 looks like the unit quaternions across the unit quaternions divided by Z2 acting by, this is just the diagonal minus 1. And so if you write the imaginary octonions as the imaginary quaternions direct sum the quaternions, then the transformation given by a pair of P and Q on U and V is Q, U, Q bar, and P, V, Q bar. That's the action. If you multiply both P and Q by -1, then you get the identity. So for the second factor, this is just the adjoint representation of one copy of this is really the usual SO3 representation of SP1 divided by Z2, and this is a standard right-left representation of SO4 on the quaternions. Okay, this is the usual. So in particular, one thing you see is that if you multiply U on the right times V, it's preserved by this representation. So that is, if I multiply this imaginary quaternion by this quaternion and think of it as, again, a quaternion in this slot, then that multiplication is equivariant with respect to this action. And what that's going to mean is that when you have an associative three-dimensional manifold in a space with G2 holonomy, there is Clifford multiplication of the tangent vectors on the normal space. This will be the tangent space. This will be the normal space. And therefore, there's a certain Dirac operator defined. I'll come back to that later. Okay, so now, given this, the question is, what's the differential equation that governs the associative manifolds? So now we have this notion of associative 3 manifolds in R7 equal to the imaginary octonion. So these are sort of interesting manifolds, right? They have the property that they're three-dimensional submanifolds of R7, and their every tangent plane is the imaginary part of a quaternion subalgebra. It's a kind of interesting condition. And you might think that such things don't exist. So the first thing to do is to imagine that that you want to graph this. So every associative 3-plane is, after you multiply by an element in G2, equivalent to the imaginary. When I decompose the imaginary octonions into the imaginary quaternions plus the quaternions, every associative plane can be brought by G2 to one like this, okay? And so let me fix an open set in the imaginary quaternions and think of a function mapping this into H, a C1 function, and then consider the graph. Let's let M3 be equal to the graph of F in IMO. So I take a domain in here and look at the graph of this function. Now, there are two operators I want to define. First of all, there's an operator D on F, which is defined as follows. This is essentially the sum. Let me be sure I get my signs right. Well, let me just write down the theorem. The theorem is that the graph equal to the graph of F is an associative submanifold if and only if F satisfies the differential equation, which looks very much like the special Lagrangian one we saw, namely a certain first-order operator is equal to a certain, this is a linear operator, is equal to a cubic first-order operator. And these two operators are defined as follows. df is by definition minus df dx1 times I minus df dx2 times j minus df dx3 times k. And you can think of this invariantly as the sum of, maybe I'll write it this way, del ej f times ej bar summed over any oriented orthonormal basis. That makes it look a little bit more invariant. Okay? And so this is some sort of Dirac operator. And sigma f, on the other hand, is more like the Monge-Ampere operator, is df dx1 cross product df dx2 cross product df dx3, or if you like, you can take any oriented orthonormal basis and write it out. Del E1f cross del E2f cross del E3f for any oriented orthonormal basis. Okay. Now, why is that? Maybe I'll say just briefly how you compute this. It really suffices to suppose, we can suppose f is linear. And then we look at these vectors. X is equal to I plus, how did I use this element E? Well, say plus f of I. This is sitting in the imaginary part of the, this is sitting in the first factor, and this is sitting in the second factor. Y is equal to j plus f of j, and z is equal to k plus f of k. Okay? And then df is simply going to be minus f of I times I minus f of j times j minus f of k times k. And sigma f is going to be f of I cross f of j cross f of k. So now you know that a plane is going to be associative if and only if the triple cross product vanishes. So you do a calculation. And the calculation shows you that if you take x cross y cross z, then this is equal to, in these terms, some sort of imaginary quaternion. And then in the second factor, you get exactly df minus sigma f. Okay, so what we want is that this be equal to 0, and it will be equal to 0. So x cross y cross z equals 0 certainly implies that df minus sigma f, well, df equals sigma f. On the other hand, if df equals sigma f, then that implies that the imaginary, that implies that the triple cross product is contained in the first factor, the imaginary part of h. Okay? But it turns out that it's not difficult to see that, well, from the fact that these things are alternating, that x, y, and z are all perpendicular to x cross y cross z. And x, y, and z, when you project them onto the first factor, give you a basis. So the imh component of x, y, and z are I, j, and k. And so if they're so this guy lives in here, but it's got to be perpendicular to I, j, and k. Therefore, it's 0. Therefore, x cross y cross z equals 0. Okay, so this is just a calculation, right? Once you get this calculation, then it sort of has this form. The main thing is that this is exactly what appears on the right. Okay? Okay, so now there's a question of existence of solutions to this, and again you can apply various methods to see that there do exist solutions to this system of equations. It's a very nice system. But another thing you can apply is Cartan-Taylor techniques. And so by Cartan-Taylor theory, we know that implies that every real analytic surface, two-dimensional submanifold, in the imaginary quaternions is contained in an essentially unique, that is, the germ of it is unique, in an associative three-manifold. So there are lots of them. Lots and lots of these guys. Take any real analytic surface, and then there's always an associative real analytic, of course, three-manifold containing that surface. So it's very rich and flexible geometry. Now, somebody asked me about this yesterday, and how do you prove this? How does it work? And it turns out that years ago, when Reese Harvey and I wrote this paper, this was an issue. There weren't these beautiful notes of Chern and Bryant and around, And so we wrote a little appendix, which was never published. So I'm going to have it duplicated. If you're interested, it's a little sort of 12-page appendix that really explains the Cartan-Kähler theorem and how it gives you solutions both in the complex and in all these cases. Okay, so there are lots of these guys. The next thing to do is to look at what's called co-associative geometry. So now I want to for this, I want to look at a four-form, and the four-form is just going to be, the imaginary. It's going to be basically the real part of this. So I'm going to look at a four-form in the imaginary octonions defined by saying that psi of x, y, z, and w is the inner product of x with a threefold cross product, y cross z cross w. So this is very much like what we did before, right? Here it was just the product. Now I'm going to take the threefold cross product. So that's the definition. And this is called the co-associative four-form. And it's a calibration for exactly the same reasons. And we have the fact that psi on x, y, z, w squared plus the imaginary part, 1/4 the length of the fourfold co-associator inequality squared is equal to x wedge y wedge z wedge w squared. So this is definitely a calibration. This number is less than or equal to 1 when you choose, a unit simple vector, and it's equal to 1 if and only if, well, it's equal to plus or minus 1 if and only if this co-associator vanishes. So this is a calibration, and it's defined by the vanishing of the co-associator. But one of the interesting facts here is that it's intimately related to the one we just looked at. So, namely, if you take the Hodge star in R7, take the Hodge star of the associate of this three-form, you get some four-form. And by the way, it's got to be G2 invariant because star just depends only on the orthogonal structure. So if you take star of phi, you're going to get, again, in fact, I think in general principles of calibration, and it's going to be invariant under G2, which this one manifestly is, and in fact, they're the same. Now, remember that the Hodge star operator in the exterior algebra is something which, when you take a simple vector which corresponds to a p-plane, gives you the simple vector corresponding to the n minus p plane, which is perpendicular to it. Right? It's the complement. It's just the thing that takes planes to their complements. So it maps the Grassmannian of p-planes to the Grassmannian of n minus p planes by taking orthogonal complement. And so this says that a plane is co-associative if and only if its orthogonal complement is associative. So the co-associative planes are exactly the normal spaces to the orthogonal complements of the associative planes. And certainly this means that this complementation process gives you a G2 equivariant isomorphism between these two spaces. Equivariant. So again, it looks like G2 divided by SO4. So these are really kind of complementary, but of course the underlying geometries are not. The submanifolds that are determined by this, whose tangent planes are these four planes, are quite different. So again, there's an equation, but I think I won't write it down. There's an equation if you have a map from an open subset in H into the imaginary quaternions, then there is again some sort of Dirac operator, and there is some sort of threefold, some sort of generalized Monge-Ampere operator, and the equation that something be co-associative is of this form. Okay, so that'll be in the notes. There is one nice example, however, of this, which is worth mentioning. So this is an example that Bob Osserman and I found years and years ago, and when we were looking at these things, Reese said, "I wonder if that thing could be calibrated," and it turned out it was. So I want to define a map. I'll call it capital F from the quaternions. Well, I'm going to make it from S3 into S2. This is S2 with radius square root of 5 over 2. And it's defined as follows. I take any unit vector in the imaginary quaternions. So I assume it has unit length. And then F, and I take a quaternion, a unit quaternion, and its image is, I think it's the square root of 5 over 2 times Q, U, Q bar. I got it right? No, Q bar. That doesn't really matter. No, it matters. It matters. Okay? So this takes unit quaternions into unit imaginary quaternions. If you take the bar of this, this is still imaginary. And this is nothing but the Hopf map from the 3-sphere to the 2-sphere. But it has a certain normalization factor. Okay? And then you can look at the graph. Let's let M4 be equal to the graph of F. And it turns out that this is co-associative. Oh, sorry. So what I want to do is to take the cone on this. So F tilde now maps all of H into MH is just the cone on this. So F tilde of Q is equal to square root of 5 over 2, 1 over length of Q, Q bar U, Q. It's just the cone on the Hopf map. So I have a map from the 3-sphere in R4 to the 2-sphere in R3, so I can just cone it off, right? And this is what it looks like if you do this. So the fact that this is now a four-dimensional manifold outside the origin. It's also a cone. It's singular, and so this is a nice example of two things. First of all, it's a co-associative variety which is not regular, but furthermore, it's a graph of a function. Now, general regularity theory tells you that if you have a C1 function which satisfies the minimal, which is minimizing in this sense, then it's actually real analytic. And this function is not C1, but it is Lipschitz. So this is an example of the fact that you cannot get that Lipschitz functions whose graphs are minimal, in fact, globally minimizing, are not necessarily smooth. Right, this thing is really singular. So it's a cone, but it's a graph of a function. All right. All right, so let's So the next geometry is Cayley geometry. So let me do that. Cayley geometry. I should probably use running out of white chalk. Okay, so now if you come back to the board, I mean, what we want to do is to define a 4 form, wedge 4 of the octonions, by saying that phi of x, y, z, w is equal to x inner product with y cross z cross w. Okay, it's the real part. Where is it? It's the real part of this fourfold cross product. And so again, this is a calibration. This is called the Cayley 4 form. And again, you have this equation that phi squared plus the imaginary, well, plus, what is it, 1/4 x, y, z, w squared is equal to x wedge, y wedge, z wedge, w squared. So you clearly get that this is a calibration, and the Cayley 4 planes, the 4 planes associated to this, are defined by the vanishing of this co-associator. Now, in fact, well, I just erased something I shouldn't have erased. Maybe I'll say it. So what I just erased, if you caught it, was an equation which was exactly that equation, except it was the co-associative 4 form. And so you might guess that if you take this 4 form and restrict it to the imaginary quaternions, that you would get the co-associative 4 form. And that's right. There's another thing you can do, and that is not to first contract with the unit and then restrict to the imaginary quaternions. Then you get a 3 form. And you might guess that that's the associative 3 form, and that's true. So a very pretty fact is that this 4 form is nothing more than 1 wedged with the associative 3 form plus the co-associative 4 form. So if you restrict to the imaginary quaternions, this dies because you have 1 here. Okay, if you contract with 1, this dies because it doesn't see the unit. This is defined only in the imaginary part. So somehow when you put these two things together, you get this, or if you like, this form sort of defines these two. Now it turns out that the space of the Grassmannian of Cayley 4 planes has a great deal of invariance, and in order to see that there's invariance, you have to use those Moufang identities that I mentioned. But you can see that in fact, spin 7 acts on this space. Now, spin 7 is the group that's generated by, what should I say? If you take a unit imaginary Cayley number, okay, then if you look at u times ux for any x, okay, this is only 2 elements. So this is the same thing as u times ux by the theorem of Artin, but u squared is -1. So this means that for every unit vector, and so more generally, if it's not a unit vector, what you get is minus u squared x. And this is the defining relation for a representation of the Clifford algebra on 7 generators. And therefore, it generates a representation of the spin group. And now what you have to do is to check that so multiplication by these by the U's generates a spin 7 action on R8. Okay, now spin 7 is a twofold covering group of SO7, and one can check. All you have to really do is to check that that this multiplication preserves the Cayley form, and that's not so difficult to do. So it ends up that this is actually invariant under the group spin 7, and spin 7 acts transitively on it. The isotropy subgroup is something of the form sp1 cross sp1 cross sp1 divided by z2. So this is again a homogeneous space, and it's a homogeneous space under the action of spin 7. Furthermore, this form actually, if you look at the subset of the orthogonal group that as Robert has said, that preserves this form, that is spin 7. So it's another definition of spin 7. And now, in this case, there's also a differential equation. Well, maybe I should just leave this up. There's a differential equation. But maybe more interestingly, I'll just tell you what the Cayley planes are, because they have several nice characterizations. So suppose I have a unit or a unit-oriented plane, but I'm going to forget about the orientation for the moment, and I want to know that this is an element in G4 of the octonion, so it's an oriented 4-plane. Then plus or minus C is Cayley. It's a Cayley 4-plane if and only if, when you take X cross Y cross Z, the triple cross product maps triples back into the plane. This plane is invariant under taking triple cross products. That's absolutely clear from the definition, right? Because if you take if you take XY, XZ, you get something which is a unit vector, if that's an orthonormal triple, and then its inner product with something, with what's left in the plane has to be 1, so that's it. It's back in the plane again. Now, if you come over here and look at what I was saying before, if U is a unit vector, then JU mapping the octonions into itself, defined exactly this way, is a complex structure. JU of X is equal to U times X. This is a complex structure. Its square is -1. Every imaginary, this is for an imaginary octonion. Every imaginary unit octonion gives rise to a complex structure. Okay? So there are lots and lots of complex structures. And the claim is that, whenever you take, and the claim is that this is a Cayley plane if and only if this is complex with respect to J, the complex structure associated to the unit imaginary quaternion, the unit quaternion X cross Y, this is always imaginary, for all X, Y, and Xc. So it's invariant under the triple cross product, or it's complex with respect to this whole family of complex structures. Whenever you take a pair of elements in here, we'll take them orthonormal, so this is now a unit imaginary quaternion, and you get a complex structure. This should be a complex 4-dimensional, a complex 2-dimensional subspace. And another nice another nice characterization is that when you take the Kähler form associated to a particular complex structure, so let's look at the Cayley-Dickson process. The Cayley-Dickson process tells us that the octonions can be written as the quaternions plus the quaternions again. So the nice way to write this is that it's the quaternions times some vector E. This is spanned by 1 ijk, and this is ijk times some additional element. And so I can look at with this decomposition, I can look at the almost complex structure JE, and it has a Kähler form okay? And the claim is that that particular Kähler form, restricted to C, is anti-self-dual. So you fix this Kähler form associated to that complex structure, then the four planes that have the property, not that omega restricted to it they're not necessarily complex, but this Kähler form should be anti-self-dual when restricted. The eigenvalues are equal and opposite. As a matter of fact, it turns out that phi, this calibration, can be written as, what is it, 1/2? Yeah, minus 1/2 omega wedge omega. Now that's already a calibration, right? Plus, this is the standard Kähler calibration, 1/2 omega squared, and here is the associated special Lagrangian calibration. You take the sum of them, well, the difference of them, and that's this four form. Now, I've chosen a particular almost complex structure, but in fact, this whole thing is invariant under spin, and when you apply an element of spin, you move this distinguished element around. So in fact, this is true. This representation of the Cayley four form holds for any almost complex structure of this kind. Okay. So now again, there's a differential equation which I think I will not write down. It's just like the one that the ones before. It's got yet another wrinkle to it, but it's a Dirac. It's again a Dirac operator. You have a function from H to H, or from an open set in H to H, and there is an equation of this sort. Again, some Dirac operator and some sort of triple cross product Monge-Ampere operator that have to be the same. Okay. So there are, and by the way, there's one thing to say. Maybe I should mention this. So there is, again, a theorem of this kind. You take a function, and so this can be replaced by some open set, and you have an equation of this kind. But this Dirac operator, there's another Dirac operator, d bar, which you get by just sort of changing the signs.
Here you also have a third operator.
There is a third operator, yeah, that's right. But the third operator is generically doesn't count. It's only there when there's some degeneration, right? Yeah, there's a second equation which for generic functions is automatically satisfied, but in certain cases it's not. But there is a sort of conjugate Dirac operator with a property that this is simply equal to the Laplace operator times the identity, and that allows you to write f as d bar of g, and then what you get is that the Laplacian of g is equal to sigma on d bar g. So you think of g as a potential, and the point is that now you can apply implicit function techniques, as I did yesterday in the special Lagrangian case, to this second order equation, and show that there exist lots and lots of solutions. But of course, we already know there are lots and lots of solutions because all the associative and co-associative manifolds are in there. Well, Yeah. Okay, so what I'd like to do now is to talk about what happens when you globalize to manifolds. So for this, so as Robert has explained, there do exist these beautiful spaces with G2 and spin 7. Well, first of all, there exist due to Yau and Calabi lots of spaces that have SUN holonomy. And we now know that there exist lots and lots of manifolds with G2 and spin 7 holonomy. And so if you have SUM holonomy, then you can talk about special Lagrangian submanifolds. If you have G2 holonomy, then that means that there exists on this space this 3 form and this 4 form, which is star of the 3 form. And these forms, as you know, play a big role in actually finding G2 manifolds. And so you have the associative and co-associative submanifolds. And when you have spin 7 holonomy, then you're going to have Cayley. So you have this 4 form, and you have Cayley submanifolds. And the big question is, do there exist, now we know that there exist, compact examples of these creatures, do there exist compact submanifolds of associative, co-associative type? Or in Calabi-Yau manifolds, do there exist special Lagrangians, which are compact? And what's the moduli space of these submanifolds? So one of the important questions about moduli space of submanifolds goes back to Robert McLean, and it's really a beautiful study. So I wanted to tell you a little bit about that. So let's do the special Lagrangian case. So suppose that Mn is an oriented, special, compact, special Lagrangian submanifold of X equal to an n-dimensional Calabi-Yau dimensional manifold with SUN holonomy. Okay? And then here's the theorem due to Robert McLean. It says that the moduli space of all special Lagrangian submanifolds in a C1 neighborhood of M naturally forms itself a C infinity, in fact, a real analytic, a CO manifold of dimension equal to the dimension equal to the middle Betti number. Sorry, the first Betti number, B equal to B1 of M. Let me say. The space of harmonic one forms. And in fact, its tangent space is naturally identified with the space of harmonic one forms. I'll write it that way. The space of harmonic one forms on M. So not only can you identify the first order deformations of a special Lagrangian manifold, but all the first order deformations actually can be integrated up to one parameter families. So this is the analog of what happens in complex analysis, right? If you have complex submanifold, then you can think about the space of deformations of that submanifold, and the first order deformations are a certain cohomology group, finite dimensional cohomology group when everything is compact, but that's not necessarily, that's only somehow the Zariski tangent space to the variety. The variety of the moduli space may be singular, and you can't fill it out. In this case, the moduli space is regular, and this is really the tangent space to it. So it's a particularly nice situation. Special Lagrangians, if you start with a special Lagrangian manifold, then it always moves in a family. Okay. And so I wanted to indicate a little bit about the proof of this, because I think it's really nice. Well, do I have the time? So I'm going to have to be a little sketchy. Here's the submanifold, M. Then there's a neighborhood of this submanifold. I've got all this color, I might as well use it. There's a neighborhood of this submanifold with the property that the exponential map from the normal bundle is injective. Okay, so there's a neighborhood of the normal bundle and a neighborhood of the manifold such that the exponential map is a diffeomorphism between the two. And now I remind you that the normal bundle, the cotangent bundle of M by the metric is canonically identified with the tangent bundle, which, because it's special Lagrangian, because it's Lagrangian, if you multiply by I, this becomes the normal bundle, which is identified, this is an identification, identified with the conormal bundle, if you like. Okay? So the normal bundle, well, I don't really need this to be, well, yeah. So now if I take a normal vector field, then the exponential map will map me. So if I have a section of the normal bundle of M, then x v, which I'll call M sub v, is in this neighborhood U. And furthermore, every manifold which is close to your given one in the C1 topology will be of this form. Okay? Because close in the C1 topology means, well, among other things, it means this. Okay? That's one way of saying what it means. So now, the point is that there's now a map from one forms on M to two forms on M, direct sum n forms on M, given as follows. If I have a one form, well, a one form is the same as a normal vector field. Okay? So you take the one form and you exponentiate it, and you pull back by the exponential map. Well, you pull back the Kähler form, and you pull back the form phi, psi, where psi is the imaginary part. I'll just write it this way, of dz. Remember? So these are the two globally defined forms. This is the imaginary part of the section of the canonical bundle, and so this is a parallel form. This is a parallel form. You pull them back, and I'm going to call this map psi. And what you're interested in is psi inverse of 0. So you see that MV is special Lagrangian if and only if psi of V is equal to 0, 0. Okay? So the special Lagrangian submanifolds are precisely now identified with one forms Okay? It's a subset of one forms, small in the C1 topology, that have this property, that when you apply this mapping, they go to 0. So it's the inverse image of 0, 0 under this map. So now what you'd like to do is to see what happens when you take a one-parameter family of these things. And well, it's in the notes. So I'm not going to have time to do it. So now what you want to do is to compute ddt of psi of tv, t equals 0 for any v. And it's really not a hard calculation. It'll be in the notes. It's not that difficult to see. But what you're going to get, of course, will be a 2 form. And the 2 form that you get is, I think it's minus. You think of v as a 1 form, take its exterior derivative. And now there's also an n form. And the n form that you get is you take star of the 1 form, and then you take d of that. Okay? So this is a calculation. And you see precisely that the linearization of the space is, and so you get that this is equal to 0 if and only if dv is equal to 0 and d star v is equal to 0. And d star v, which is plus or minus star d star v, is equal to 0. In other words, it's a harmonic form. It's a harmonic form. And now, in fact, you can think of this as mapping not just now you can apply Banach space techniques, and you think of these not as C infinity 1 forms, but you think of them as 1 forms in C1 alpha. Okay, that's a Banach space, and it maps to forms of this kind, which are of type C0 alpha. Okay, now there's some hope for that to be an isomorphism. The only problem is that you're not going to get all forms because, the image is going to be closed here, for example. And in fact, they're both closed. What you can show is that the image is always into exact forms. That's sort of easy because the exponential map is homotopic to the identity, and the identity pulls these guys back to be 0, the inclusion. And the inclusion pulls these things back to be 0 because it is itself special Lagrangian. So this maps into the exact forms. Exact. Okay, and now you can apply, and now the linearization of this is in fact onto, and so you can apply implicit function techniques for Banach manifolds and conclude that locally the inverse image of 0 under psi is a submanifold whose dimension is exactly equal to the dimension of the space of harmonic 1 forms. Okay. So this is a wonderful result. It also works in the co-associative case. In the co-associative case, the tangent space becomes. This doesn't come down. In the co-associative case, the tangent space is the space of co-associative. You look at the harmonic. The harmonic 2 forms. So a co-associative manifold is a 4 manifold. Okay, so there the tangent space to the deformations consists of again harmonic 2 forms, but the harmonic 2 forms which are anti-self-dual. The anti-self-dual harmonic 2 forms. That means star of the 2 form is minus the 2 form. In the associative case, it's not so simple. Oh, and by the way, in this case, the moduli space is again smooth. It's always smooth. You really get a smooth moduli space. In the other two cases, in the associative case, it turns out that there's a certain Dirac operator that I alluded to, and it's the kernel of this Dirac operator is the tangent space. But in this case, you don't know that the moduli space is smooth. And the same thing in the Cayley case. There's a certain Dirac operator. So you can compute the first, you can compute the sort of Zariski tangent space to the deformations, but it may in fact be some singular thing. The general picture is that in this tangent space, the moduli space is some subvariety. And that subvariety is everything only in certain circumstances. Okay, so the last thing I wanted to say, and I have just enough time to say it, is that there's a general picture which should unify and extend, I think, what Robert's been saying and what I've been talking about. And that is that there's a very nice relationship between spinors and calibrations. So I have to say this, I have to say one or two words about Clifford algebras. And now I'm going to make life really easy in this case. So for simplicity, I'm going to assume that V is a vector space of dimension 8K, because Clifford algebras are particularly simple, and spinors are particularly simple in dimensions congruent to 0 mod 8. And I assume that it has a positive definite inner product, as usual. Okay? And then there's something called the Clifford algebra of V, and this is the algebra which is generated by unit and, let's say, an orthonormal basis, the standard orthonormal basis of this space, subject to the relations EI, EJ plus EJ, EI is minus 2 delta IJ times the identity. Okay? That actually generates an algebra. And these are intimately related to the complex numbers in the quaternions. And it turns out that this algebra is isomorphic to the exterior algebra of V as a vector space. As a vector space. But what's really true is that this algebra is this algebra is filtered. It's filtered by sort of the number of products that you have. And this is the associated graded. You see, the exterior algebra is what happens when you make this 0. If you make this 0, you get the exterior algebra. And but this is a canonical isomorphism between these two, and this is an important fact. So, if I take an orthonormal basis, then E1 Clifford product EP, this corresponds to E1 up to, if these are really orthogonal, mutually orthogonal. Okay. Now the basic fact is that the Clifford algebra arises as the space of endomorphisms of another vector space. So the basic fact is that the Clifford algebra of V is equal to the space of, or if you like, canonically isomorphic to, the space of endomorphisms over the reals of another vector space, S, where S is a real vector space of dimension 16 to the power K. Big. So these spaces get huge. And they sort of, they need to. And now there are three basic facts. There exists an inner product. I'll put an S on it, on this spinor space with a property that ES prime, well, I should call this sigma, is equal to sigma sigma prime. That multiplication by unit vectors, when I take a unit vector in V and let it act, it gives rise to an endomorphism, then that unit vector acts orthogonally with respect to this inner product. The second thing is that there exists an inner product on the Clifford algebra, okay, which is given as follows. AB is simply the trace of A transpose composed with B. This is the usual inner product on endomorphisms. So here I'm thinking of the trace on S. And thirdly, there exists an inner product, which I'll write as lambda, on CL of V. Well, this is the L on CL of V, lambda star of V, the usual L2 inner product. Okay, so you take the usual L2 inner product. And now there's a little lemma which is that if I take A and B Clifford inner product, this is equal to 16 to the k times the standard inner product. And you can sort of see this. Yeah, it's a much longer. Yeah. Anyway, they're the same, but there's a factor, and this factor is very easy to compute, actually. Now, this is the main principle. This is the main thing that I want to say. The square of a spinner is always an interesting calibration. Calibration. Oh, family of calibrations. So what do I mean by this? Let's suppose I take an element in the spinor space. I'll call it sigma. Okay? Then whenever you have an element in a space with an inner product, there is this stupid rank 1 endomorphism that you can get by just projecting on that line, right? So then I'm going to define sigma dot sigma in the Clifford algebra of V, which I remind you is the endomorphism algebra of S, by letting this be just projection on that line. So what does this mean? This means that sigma, when it sees a spinor tau, you take the inner product with tau times sigma. Right? That's exactly what you do when you project onto a line. So this is the simplest of all possible endomorphisms. Right? Take a spinor and look at this simple endomorphism. But now it's an element in the Clifford algebra. And the Clifford algebra is identified with the exterior algebra. So this is a whole batch of differential forms. Okay? And there's a little lemma. Again, I don't have time to prove this, but it's in the notes. And that is that if I take a form phi and I pair it in the Clifford inner product with this squared spinor, this is the same thing as sigma inner product with phi dot sigma. Okay, that's an easy calculation. Okay, but now you see, if this is a simple vector, then this is just multiplying by a simple vector. And when you multiply by a simple vector, that's an orthogonal transformation. So if you start with a unit spinner, you multiply it by multiply it by an orthogonal transformation, then this inner product is going to be less than or equal to 1. So this thing, as a differential form, is a whole set of calibrations. So given that, now there's a little point here, namely that there was this factor of 16 to the k. So the claim is that then if you take this form and decompose it, so let's let n be equal to 16 to the k, and suppose that sigma has unit length, then n times sigma decomposes as a sum of forms, k equals 1 to little n psi k, where psi k is in wedge k of v. And the claim is that each of these is a calibration. Each of these is a psi k is a calibration for all k. So it's really, really straightforward and easy to see. And now, furthermore, there's a lot you can tell from this because, for example, you can see that exactly what the Grassmannian of this creature is. It's sort of, it's exactly equal to those xi such that xi times sigma is equal to sigma, because that's when this inner product is going to be satisfied. It's going to be equal to 1. And furthermore, if you look at the subgroup of the orthogonal group of the vector space that fixes sigma, it's going to fix sigma dot sigma, and so it's going to fix all of these forms. So the symmetry group, the group of orthogonal transformations fixing this spinner fixes all of these forms. So it's nice to look at spinners take a spinner whose isotropy subgroup is maximal. These spinners were looked at by Cartan, who called them pure spinners. The pure spinners are the ones with maximal symmetry. And every time you have a pure spinner, you get a very nice calibration with a large symmetry group. So and in global terms, what this means is the following. If you have, on a Riemannian manifold, a parallel spinner field, then square the spinner field, take its various components, and you have parallel differential forms, a whole lot of them. And every one of those forms is a calibration. Furthermore, you know exactly what the Grassmannian is at every point. It's given in this nice way. So let me just finish this with the bottom example. The bottom example is given by let's look at k equals 1. So we're looking at R8. So now it turns out that the spinner space is of dimension 16, but it decomposes into two spaces which are invariant under this spin group. This is sort of S plus and S minus, and these are both 8-dimensional. So these are all 8-dimensional representations of spin 7. And no, spin 8. What am I saying? No, spin 7. And no, spin 8. Spin 8. Yeah, spin 8. These are all representations of spin 8. And so I can take a spinner that sits here. Now, by the way, spin 8 acts transitively on all of these. It certainly acts here in the usual SO8 representation. And then these sort of differ by outer automorphisms. They're really very, very closely related. And so if I take an element here, all unit vectors here are equivalent because the group is acting transitively. So I just take one. It doesn't matter. Call it sigma, and let's square it. Now I've got a differential form. And the differential form has a component in dimension 1. it has a component in dimension 4, and it has a component in dimension 8. And guess what the one in dimension 4 is? It's the Cayley calibration. And it has to be because you see that the subgroup that fixes a vector here is the subgroup spin 7. The unit sphere in this R8 is just spin 8 modulo spin 7, which is the same as SO8 modulo SO7. And so you immediately see that this differential form constructed by general principles is invariant under spin 7. Okay? And, but now, you can construct lots and lots of highly invariant calibrations in the same way. And also you see that, well, so that's enough. Thank you very much.